Welcome to the afternoon session, Circuits, exclamation point. The first speaker is John van Wetering, and he's going to be talking about There and Back Again, a circuit extraction tale.
Thank you, Alex. So in the background, you can see my co-authors. We have Miriam here, Giovanni, Hector, and Leo. So let me start. So the paper is called There and Back Again, a circuit extraction tale, and it's about moving between two different paradigms of quantum computation. So on the one hand, we have the gate-based model, the quantum circuit model, where we start with qubits that are prepared in some simple state, and then we successively apply small unitaries, and at the end we measure the qubits, and hopefully we get the outcome that we are expecting. On the other hand, we have the measurement-based model, where we prepare some highly entangled resource state. Then we perform successive single qubit measurements on this resource state, where later measurement choices depend on earlier outcomes. And at the end, we again hope that we get the outcome that we expect. So our work is moving between these two things, where we have patterns on the one hand and circuits on the other. And the way we're going to translate between them is by using ZX diagrams as an intermediate language. So there's a few directions to this graph that are relatively straightforward. Moving from circuits to ZX diagrams is a very easy, straightforward direction. Moving from a pattern to ZX diagram is also relatively straightforward, and from ZX diagrams to patterns is also not too hard. The hard direction here is moving from a ZX diagram to a quantum circuit, which we call a circuit extraction from the ZX diagram. And what we do in our work is we find a circuit extraction algorithm, an efficient algorithm that applies to measurement patterns or ZX diagrams that have a property known as G-flow, which I'm going to talk about more. And this work generalizes a previous algorithm that I worked on with Ross Duncan, Alex Kissinger, and Simon Pedri. And then we also have this final arrow here, which is optimization of ZX diagrams. Which turns out to be an optimization of the number of qubits needed to implement a given measurement. Okay, so let's get started by describing what ZX diagrams are. I'm not going to go into too much detail. There will be a few more talks this session that will deal with ZX diagrams. So the general idea is that while circuits consist of gates, ZX diagrams consist of spiders, and spiders come in two different flavors. We have Z spiders, which are depicted in green, and we have X spiders, which are depicted in red. And they are just these two particular types of linear maps. They can have any number of inputs and any number of outputs. And the ZX diagram is simply any wiring of these spiders, where we don't really care about topology. We can move all these nodes around, and it will still represent the same linear map. If you're familiar with tensor networks, this is just a tensor network, and a wire just depicts a tensor contraction. Okay. Every quantum gate can be written as a ZX diagram. So we have an S gate, which is a pi/2 Z rotation, T gate, which is a pi/4 Z rotation. We introduce a special notation for the Hadamard gate, since it's really useful in ZX calculus. This yellow box, which you can see is defined by using this Euler decomposition of its angles. The C0 gate, CZ gate. Because we will use the Hadamard gate many times as a type of edge between spiders, we introduce a special notation for it, which is a blue dotted wire. And using this, we can very straightforwardly translate a quantum circuit into a ZX diagram. There is a complication because the native gate set for ZX diagrams is Clifford gates plus arbitrary phase rotation. So if you have, for instance, a Toffoli gate, you first need to decompose it into this gate set, then you can transform it into a ZX diagram. Okay. So any talk about ZX calculus needs to have a slide like this. It's the set of rules that make ZX diagrams useful. So these are rewrite rules that preserve the linear map that's implemented by the ZX diagram. So for instance, if we have two spiders of the same color that are connected by a wire, we can just fuse these spiders together and add the faces together. I'm not going to say too much about this, but note that we have this notation here of a pi, and this a is a variable that takes a value of 0 or 1. And we use this to denote a family of diagrams at the same time. And we need it to represent measurements, because a measurement, of course, can have two outcomes. So we can represent both outcomes at the same time in the same diagram. Okay. The select calculus has a few desirable properties. First is universality, which means that any linear map between qubits can be represented as a select diagram. So there's no limitation to what you can represent. And another property is completeness. If we take the rules of the previous slide and we add one more slide, then if we have two select diagrams that represent the same linear map, they have the same matrix, then we can find some set of graphical rewrite rules that transforms one to the other. There's a variety of different completeness results, and if I'm not mistaken, Harney will give a talk about this in a hour's time or so, about the different completeness results. It's not super important for our results, but I think it's nice enough that we mention that we have the property. Okay, so we've seen now how to translate from a circuit into a select diagram. So now let's go from a measurement pattern to a select diagram. So the measurement-based model we use is the one-way model. And this starts with a graph state. So the resource state we have is a graph state. And then in some chosen order, we start measuring qubits. These measurements lie along the three principal axes of the Bloch sphere. I'm going to say a bit more about what that is. And the measurement angle of a measurement, a later measurement, may depend on the measurement outcome of a previous measurement outcome. And we just repeat these measurements, all the qubits, until we reach the desired output state. So maybe we have like we want the output to be some 2-qubit state, so we measure all qubits except 2, and then we are left with a 2-qubit state. So I was going to see how to translate each of these components into select diagrams, into the select calculus. So graph states are very easily represented as a select diagram. So we just take the graph of the graph state, and for each vertex we just add a spider, and for each edge we just add a Hadamard edge in between them. And this is actually what we call an open graph state. So we have some input wires here and some output wires, and this just allows us to consider fragments of a measurement pattern. So where we allow measurement patterns to be composed because we have some inputs that can be put into outputs. And then we can represent measurements. So as I said, we have measurements in 3 planes. So for instance, the XY plane in the Bloch sphere is like this circle around here. And with this alpha, we can determine in which axes we are actually measuring. And this A pi, I mean the measurement outcomes. If A is 0, I consider that to be the desirable outcomes, the outcome we want to happen. And if A is 1, then we get this pi phase that's sort of undesirable, and we need to correct for it later to get the actual computation we want to implement. Yeah, so we have these 3 different measurements, and we can just compose the graph state with these measurements to get an actual measurement, pattern. We don't really write how later measurements depend on previous measurements in the select diagram. That's a bit tedious. We'll come to that later, how we do that. Okay, so we had this circuit that we translated into a select diagram. And now with some simple modifications in select calculus, if you're a bit familiar with select diagrams, this is a very straightforward translation. So this thing is a graph state where we have a lot of measurements. So this qubit here is measured in a 0 phase. This qubit is measured in a pi/4 phase. This is an output qubit, so it's not measured. Same here. And yeah, you can easily verify these are in fact the same select diagram, represent the same linear matrix. But there is a catch. I haven't written this A pi correction here, or like the outcome I get if I get the wrong measurement outcome. That's because this is the pattern I want to implement. So the question is, can we make this deterministic? Because if I get the wrong outcome here, can I do something on the later qubits that corrects for that error? And to answer that question, we need to introduce a different concept, which is flow, or G-flow. So we want to have measurement patterns that, regardless of the measurement outcomes I get while measuring the qubits, I have the same overall linear map. So I have a deterministic pattern. Now, for patterns that contain only XY plane measurements, so for instance, this thing here, which only has XY plane measurements, there is a sufficient condition that's called causal flow. It was introduced in 2006 by Danas and Schiff. For general patterns, so patterns that can contain measurements in all three planes of measurement, a sufficient but also necessary condition is G-flow, so generalized flow. Necessary here refers to a particular type of strong determinism that I'm not going to get into. You can ask me if you want to know more. But the idea of a G-flow, like what is a G-flow? It's a condition on the underlying graph that there is an ordering on the vertices, so on the qubits, that tells you in which order to measure the qubits. And it is a sort of condition on the parity of the neighbors, of the neighborhood sets of each vertex, that then tell you that any measurement error can either be fed forward to the future, or the adjacency matrix is such that the error sort of cancels out itself and we don't need to actually correct. And it turns out that the previous translation I showed you of a circuit into a measurement pattern, this always has causal flow. So we can always put some kind of corrections on it that make it determinate. Okay, so that solves one side of this translation, going from a circuit into a deterministic measurement. Okay, our main result is the opposite. It's that there is an efficient algorithm to transform a measurement pattern which has G-flow into a unitary quantum circuit. And with unitary here, I mean that we don't need any ancillas in this circuit. This extends previous work by me and some co-authors, by Ross Duncan, Simon Petit, and Alex Kissinger, which only dealt with XY plane measurements. And so our improvement is that we can actually deal with all three types of measurements. The general idea of the algorithm is that we first write the measurement pattern as a ZX diagram, and then we start slowly transforming it into a circuit, qubit by qubit. So this is a sort of illustration of what it looks like when you're halfway through the algorithm. So we have our unextracted measurement pattern, and we have our extracted circuit, and we're moving from right to left. So we're here at the frontier, and we are trying to get these qubits to come over here into the circuit part. So the way we do that is we have this bi-adjacency matrix in the graph here. And by using a Gaussian elimination type algorithm, we can sort of add CNOT gates here, and that simplifies this bi-adjacency matrix. And the goal is to simplify this bi-adjacency matrix enough that we can now put one of these qubits here over here. And then we have one qubit less in the measurement pattern. So it's one qubit simpler, and we just repeat it until all the qubits are complete. Okay, so let's go back to the overview again. I've shown you how to go from a measurement pattern into a ZX diagram. I've shown you how to go from a circuit into a ZX diagram. ZX to pattern, I've sort of told you implicitly, but it's not that hard to do. And I've now given you we have given the algorithm for going from a ZX diagram to a circuit. So now I want to say a bit more about this last bit, about optimization here. So very briefly, what we can do is, if we have a measurement pattern, we can remove any internal Clifford qubit. So a Clifford qubit is a qubit that's measured in a Clifford angle, where a Clifford angle means that the alpha, like the measurement angle, is a multiple of pi over 2. And the way we remove it is we have these operations, these graph operations called local complementation, that's the first one, and pivoting, that's the second one. The local complementation, it removes a single qubit measured in a pi over 2 or minus pi over 2 phase at the cost of complementing all the edges between the neighboring vertices and changing the phases over there. And pivoting, it takes a adjacent pair of qubits measured in a 0 or pi phase. It can remove them and then introduces some set of edges between these and also changes the phases. And we need some variations on these, but this is the basic idea for people. And then what we show is that these operations preserve the existence of G-flow. So what that means is that if we start with a measurement pattern that has G-flow, we can remove these qubits and we retain G-flow. So we still have a deterministic measurement pattern. So that means if we combine it with a translation from a circuit into a measurement pattern, that we can take an n-qubit Clifford plus T circuit, or just Clifford circuit which has some non-Clifford rotation. And if we have T of those rotations, then we can efficiently transform this into a deterministic measurement pattern, which contains T plus ON qubits. So this means that we have T internal qubits. So these are qubits that are measured in a non-Clifford angle. And we have some qubits on the border, so on the input and on the output. Okay. So conclusion of our work, we went there. So we went from circuits to measurement patterns. We went back again from measurement patterns to circuits, and we can do some optimization along the way. Thank you for your attention.
All right, thanks, Ben. So there's a bit of a lag to the Slack, so
we went there. So we went from circuits to measurement patterns.
Questions to come
We went back again from measurement patterns to circuits.
Oh, there was a bit of an echo there. I guess while we're waiting, I could ask a question. How does the extraction behave with respect to how many CNOT gates you get?
Yeah, that's it's an interesting question, and not one that has an easy answer. So on some types of circuits, we see a decrease in the CNOT count, but on many other types of circuits, we see an increase in the CNOT count. So the circuits where we see an actual benefit, so that the CNOT count decreases, is on quantum chemistry circuits. They consist of many exponentiated Pauli operators. They have sort of a very symmetric they're sort of very symmetric, and once you synthesize those with CNOT, they become asymmetric, so you lose some information. And our extraction sort of seems to capture this information, so it's able to do better. While on a circuit containing many Toffoli gates, it seems to fare much worse and actually introduce many more CNOT.
Mm-hmm. Okay, now Eddie Schoute has asked, what are the constraints on G-flow? Any hope of loosening the constraints?
So I think it's already quite general, because if you have a measurement pattern that is not deterministic at all, it doesn't implement a unitary. So that means there's no hope of getting a unitary circuit out. So you need to have a deterministic pattern. And if your deterministic pattern is what's called uniformly deterministic, so that means it's deterministic for any choice of measurement angle, then you have a G-flow. So there is like, you can gain a bit more, like if you somehow get an algorithm to go from uniform deterministic that can also handle deterministic. But I'd be surprised if there is a algorithm that can actually handle that case, because you get into territory where like being able to extract in such a general setting is like QMA hard or like PQP hard. Like it becomes a very hard problem.
Okay, great. Thanks, John. I'd invite you to go over to your chat channel and answer any other questions you get afterwards.